All right, so let's pick up where we left off with lecture 4.1. There, what we had was a linear transformation, and we wanted to compute the kernel and the range of that transformation. And so what we said was that the kernel of T was the same as the null space of A, which means it is the set of vectors in the domain. So in this case, the set of vectors in R3 for which this system is solved by that value, right? So you want to collect the solutions of this homogeneous system into a set. That's the null space of A or the kernel of T. So let's just go through our usual scheme of setting up the augmented matrix. So we have 1, 0, 1, 0, 1, 2, 4, -3, -2, and then bar 0, 0, 0. And the idea is to put it into echelon form as usual so that we can identify what the solution is. All right, so to do that, we're going to put, we already have a 0 here, so we want to put a 0 there. And so we're going to multiply R1 by -4, add it to R3 and put it into R3. But in so doing, we're going to leave rows 1 and 2 alone. All right, so we get 1, 0, 1, bar 0, 0, 1, 2, 0, and 0, -3, -6, 0. And then we want a 0 here, so let's multiply R2 by 3, add it to R3 and replace R3 by it. And notice that in so doing, we get a 0 row. Right, so a row of zeros. That is an echelon form, right? Because we have the number of zeros here is strictly less than the number of zeros down below, and all the 0 rows are at the bottom. The pivots are these guys, and so this one here is a free variable. All right, so let's call x3 s1. That's a free variable. And so if you back substitute, we have x1 plus 2s1 equals 0. I'm sorry, x2 plus 2s1 equals 0. And so x2 is -2s1. And then x1 plus x3, which is s1, is equal to 0. So x1 is -s1. And so the kernel of T is equal to the collection of all of these vectors, s1, 2s1 minus s1, where s1 is in R. Okay, but it looks a little bit better to write this as the vector 1, 2, -1 times s1, where s1 is in R, because we identify that as the span of that vector. Right, so that's the span of that singleton vector. All the scalar multiples of that vector is the span. All right, and so the kernel as being a subspace is the span of that vector. All right, for the range, we do the same sort of thing. We want to put a B on the right side, so we'll call that B1, B2, B3 as usual. We'll use the same A on the left, so 1, 0, 1, 0, 1, 2, 4, -3, -2, bar B1, B2, and B3. And we want to find if there are any conditions on these components of B that have to be satisfied in order for there to be a solution of this system. All right, so again, put it into echelon form by multiplying R1 by -4 and adding it to R3, replacing R3 by it. If I do that, you can check this out. I get the first 2 rows don't change as usual, but the third row becomes 0, -3, -6, but -4b1 plus b3. Right, so very similar to what we had up here, just that the right side is changing. And then same way we want to get a 0 here. So we're going to multiply R2 by 3, add it to R3 and replace R3 by it. And so the matrix we end up with, first 2 rows are the same. The last row is not a 0 row now, unless we have a condition, right? So the condition will be, right, the only way this system is going to have a solution is if this doesn't produce a falsehood, right? And so we need B3, so we need this whole thing to be 0, which means we need B3 to be 4B1 minus B2, 3B2. All right. If that doesn't hold, you have a falsehood, and so the system doesn't have a solution, right? So for B equal to B1, B2, 4B1 minus 3B2, right? Or if you want to write this out, pull the B1s together. So 1, 0, 4 times B1 plus 0, 1 minus 3 B2, right? For B1 and B2 in R, right? That's how you can write a general vector B for which there is a solution. Right, I'm going to pull that apart like I said I've been doing all along. That's the structure of the range of T. Notice that these two vectors here end up being those original columns of A, which correspond to the rows that have pivots, or the columns that have pivots, right? So these are your pivots. These are the columns that contain the pivots, right? And so this is equal to the span of 1, 0, 4 and 0, 1, negative 3, right? Which is the span of the columns of A corresponding to pivot locations. So we didn't have to go through all that nonsense. Once we found what the pivot locations were, we actually have the vectors that we need to generate the span that gives you the range. Okay, so that's where we ended up with that. Now let's using that, we're going to use that as a prime example in this section. That's why I wanted to hold off on it in the lecture. All right, so notice here that technically, if you were to write, if you wanted the range of T, what we could have simply said is take the span of all three, right? Technically, because then any linear combination of these two guys would be in that span, just multiplying that column vector by 0. And so it would do the job. It's just you have a lot of extra stuff in there that's going to be redundant, right? And so in this case, what you wanted to do is, while the range of that linear transformation is in fact the span of those two vectors, I could have said it's the span of these guys and not have to go and worry about the exact number of vectors that would have done the job, right? Certainly that is equal to the span of just these two, right? So if I just use these guys, right, we already know the span of this is the range. And so if I clap another vector in there and take the span of that, it's not going to change the span, right? So what I would like to do, though, the number of the vectors that you use to span a subspace is actually important. And so what I want to do is find what would be called a minimal spanning set. We want to find the set of as few vectors as possible so that the span of that set generates the space you're after. So here, this would be a minimal spanning set of the range of T because there were two variables that you needed here, right? So one of them couldn't do the job because you can't generate everything with just scalar multiples of this guy, right? Because there's a 0 there and a 0 there. And so you have to make sure there's a relationship between these two, namely that they're linearly independent. But if they were dependent, then you can rewrite one as a scalar multiple of the other, and so you'd only need one of them to span the whole set. So here, we're going to call a set, we're going to look at sets that contain as few number of vectors as possible and still span the space, and for which those vectors are linearly independent to ensure that I couldn't have thrown one of them out to begin with. All right, and so we're going to define a new word called a basis that means just that. All right, so a set of vectors, we'll call it B for basis. Oops, it's a little bit larger, pull it down. It's a basis for a subspace S if what I said just happens. It spans S and the vectors are linearly independent. All right, so it's a linearly independent spanning set. All right, so back in our previous example, when we were looking at the kernel and whatnot, look at this. The reason we wrote it like this is so that we can actually see that guy. How many vectors do you need to produce that if you took it the span? Well, we only needed this guy. So the basis for the kernel of T would be that vector alone, that singleton vector. The basis for the range of T is that set of vectors right here, right? You can actually show they're linearly independent because they're not scalar multiples of each other, right? It's fairly easy to see that. And so that would be a linearly independent spanning set or a basis for the range of T. All right, and so here you can have a lot of different bases, right? You can multiply, you can turn things, right? So if you rotate everything by any angle, those generate vectors that are still linearly independent, but they're different vectors, but they'll still span because they still are linearly independent. And so it's the number of vectors in the space that you want that are of interest. And so note this, that no matter what basis you take of a subspace, the number of vectors you need can't change. It's always the same because a basis has the minimal number of vectors in it that would span the space. All right, so the number of vectors in the basis is called the dimension. And so here, in terms of dimension, the kernel, the basis for the kernel contained a single vector, so its dimension is 1. The basis for the range of T contained a single vector, contained 2 distinct linearly independent vectors, so its dimension is 2. All right, so for these 5 examples, we just want to determine if they are if each of them forms a basis for R2. What you need for a basis, again, 2 things. The vectors have to be linearly independent and they have to span R2. So right off the bat, we can get rid of 2 of them, right? This guy cannot span R2 because you're only taking linear constant multiples of 1, 2. So the span of 1, 2, here x is 1 and y is 2, is this line, right? So that's not R2. This would be a basis for this line, remember, because those lines to the origin are subspaces of R2, but it's not a basis for R2. It doesn't span R2, and so that's no. And then these guys, well, it's a spanning set, I agree, because if you note here, those are the 2 typical basis vectors that you think of with R2 along the x and the y axes. Here's 0, 1, 0, and 0, 1. And we already know from various settings that those 2 vectors are certainly linearly independent. You can't multiply one by a scalar to get the other. And they do span, right? Any vector can be written as a linear combination of those guys. And so this guy is a yes. But since that spans, this can't be a minimal spanning set. It contains that vector. And so this is not linearly independent. In fact, the third vector there is the sum of the other 2. So in a big way, it can be written as a linear combination of 2 of them already in the set. And so it's not a basis. This guy, if you look at it, 3, 6, is a scalar multiple of the other vector. It's 3 times it. And so these are not linearly independent. And so that's not a basis. They have to be linearly independent and span R2. This will span the same thing as that guy, right? So the span of that set, if you throw in both of these vectors, is the same as the span of that. It's that line. Okay, these 2 guys, they are linearly independent and they do span, right? So you can actually conclude that yes, indeed, that spans R2. And, the linear independence is easy to see because we know that you can't multiply whatever you need to multiply this guy by to get 3 here won't work to get you 7, right? And so they are definitely independent. But to see that they span R2, you would have to show that this has a solution for all B1 and B2, right? In other words, give me any ordered pair in R2 with those components, that system has a solution, right? And so if you can easily show that by just putting into echelon form and solving it that way. So it indeed is a basis. All right, so it's not a big deal. It's things that we've already been dealing with, but now we're just trying to get rid of redundancy and just say, okay, we only this many vectors and here they are. And we know that those guys are a basis. They're a bare bones skeleton that will be formed by multiplying them by scalars and adding them together to generate the whole body, so to speak. Okay, so here's a big theorem, and it's not hard to prove actually, as it turns out, but it's a very big theorem. Of course, you can't see it. All right, so this is the big theorem I'm talking about. Give me any basis for S. So if B is such a basis, every vector in S can be written in a unique way as a linear combination of elements of B. And the key here is unique way, right? The existence is easy, right? If B is a basis for S, that means that the span, first off, of B, so the span of those vectors has to be S, right? Well, then give me anybody in S. If that's the span is the set of all linear combinations of those guys. So certainly the existence is fine, right? You can rewrite any element of S as a linear combination of those. The uniqueness follows because of the linear independence, right? So we did this way back in chapter 3. Suppose that when we were dealing with one-to-oneness, and we said, well, suppose that there were 2 different ways of writing that out. And then you showed that if you took 2 different representations for the same element and subtracted them, you got 0 back, which meant they were the same to begin with. And so the uniqueness follows, I won't rehash that, it follows from the linear independence of the U guys. Okay. All right. So that was just, I just kind of chatted above it up there. All right, so let's go through this. Suppose I gave you 3 vectors, and I remember the span of vectors is a subspace, right? So here, these vectors belong to R3. So I know without doing anything else, I already know the span is a subspace of R3. What I want to do is for that subspace, I want to find a minimal spanning set. So I want to find as few vectors as possible so that when I take the span of those vectors, I get back this subspace. And so there are 2 different methods. The justification's a little bit more theoretical than I'm going to go into. It's not hard, but you really have to wrestle with it a little bit. And so I'm going to leave this off. It's good for you to read, good food for the mind. I will have you read this on your own, right? And perhaps watch a YouTube video on it just to kind of get an idea. But it's kind of shuffling and using row operations and independence to kind of see that things don't change, right? But I'll let you read that. But if I gave you these 3 vectors and I want to find the basis for the span, there are 2 approaches you can take. So one approach is to construct a matrix whose rows are the given vectors, right? So I'm going to form kind of like this. So symbolically, I'm forming a matrix using the U1, U2, and U3 as rows, right? And so I'm just going to turn them and form that guy. And then I'm going to convert it to echelon form and then take the non-zero rows. All right, so if I want to go to echelon form, I want to put zeros there and there. So I want to subtract R1 minus R3, put that into R3, and R1 minus R2, and put that into R2. The first row remains unchanged. The next one, if I do that, I get one, let's see, one, a -1, I can't read anymore, -4, and then 0, 2, -8, correct? Is that right? So if I subtract 1 minus -1 is 2, 0 minus 8 is 8. All right. Oh, that should be a -8, I'm sorry. So that's +8. All right, sorry about that. And then now I want a 0 here, so I'm going to multiply row 2 by 2 and add it to row 3 and clunk it into row 3. And so if I do that, I still have that row, but if I do that here, I'm going to get a 0 row here. All right, and so what you want, what the claim is of this approach that I'm describing down here is that these rows are the non-zero guys. They came from these vectors, right? And so we're going to use those vectors back in column form, right? So I just converted to row form for the process, but you go back to their original form and conclude that the basis for, oops, this set or this subspace S for S is that guy. Those two, that's all you needed were those two vectors to form the basis for that subspace. All right, so again, it's not a proof at all. The description is down here, but take those, convert them to rows, put an echelon form, and the non-zero rows converted back to their original column vector counterparts form a basis for the set. All right, and then the second method is to construct a matrix again, but now I'm going to use the vectors as columns, but I'm still going to put it into echelon form, but I'm not going to use, remember, I'm looking for columns this time. So I'm not so much interested in the 0 rows as I am the columns that contain pivots. All right, so they play analogous roles if you turn one versus the other. All right, and so here I have the same sort of idea. I have 1, 1, 0, 1, 2, 4, 1, -1, 8. So I'm putting these vectors in as columns. And I want to put it into echelon form still. So I want a 0 here. So subtract R1 minus R2 and put it into R2. And that'll give me 0, -1, 2. The last row didn't change. And then I want to put a 0 there. And so I'm going to multiply R2 by 4, add it to R3 and put it into R3. And that gives us still 1s across the top. That row stays the same, but now I get a 0 row. Okay, and so what we want to do is identify the pivots, right? So these guys are the pivots. All right, and so what that tells you is I want to go back to these vectors here, and those two together, just like before, they form a basis for S. So you have the same conclusion as before. Both methods will yield the same result. It just depends on which one you're more comfortable with, I would say. And that'll work no matter what, right? So anytime I have a bunch of vectors and I take their span and I want to find a minimal spanning set, you can go through that process to kind of pluck out which ones you need and which ones are redundant. And then finally, suppose if I have a linearly independent subset of Rn, right? So remember, all linear, if I just have, suppose I'm in R3 and I have 2 linearly independent vectors, that's not going to span all of R3, right? You need another one. And so what you want to do is you want to be able to start with those, right? Finding linearly independent vectors is good, right? Because you need those to form a basis in the first place. But so why reinvent the wheel? Start with those, throw in the standard basis vectors for R3. So you're throwing in more than you need, but then reduce that down using that previous process, right? Either the rows or the columns. right? If you use those as columns, then you find the pivot columns and use those as the basis. If you convert them to rows, find all the non-zero rows after you put it into echelon form, and then go back and use those vectors in column form, right? So it's a way of forming a basis for Rn, given that you're starting with kind of some part way through the process. All right, so let's take the U1 and the U2 in example 2, right? So we know already that 1, 1, 0 and 1, 2, 4, those are these vectors from example 1 that I'm talking about. Okay, that was the set that was the basis for the range of T. Well, but there are only 2 of them. We know they're linearly independent, but they can't span all of R3, right? Because there's only 2 of them. So what I'm going to do is I'm going to affix the standard basis vectors. Those are just the ones where you have a 1 on one of the components and 0 everywhere else. And you do that for every one of the components. All right, so I'm adjoining these. These are the standard basis vectors. Right, and these are U1 and U2 respectively. All right, and so I'm now going to actually go through and find the pivot columns, right? Since I'm adding on the rows or columns as it is, I'm going to use that second method of finding the pivot columns. And so to do that, I'm going to get a 0 here. So I'm going to subtract R1 minus R2 and put it into R2. So I have 1, 1, 1, 0, 0. If I subtract R1 minus R2, I get 0, negative 1, 1, negative 1, 0. And then this last column stayed the same. All right, so now I have zeros here, but I want a 0 there. So I'm going to multiply R2 by 4, add it to R3, and replace R3 by it. If I do that, the first row remains the same, the second row remains the same, and the fourth row becomes 0, 0, 4, negative 4, 1. Okay, and so now that's in echelon form. There are no 0 rows, so you identify the pivots, which happen to be right there. And so what that tells you is that if you go back here, these 3 vectors, right, so these tell you that if you go back to the columns that are in the same exact position, the span of those guys, so if I take that vector, this vector, and this vector, that forms a basis for R3. That's all you have to do. That's kind of nice. All right, so let's actually look at just some summary of some properties. So any spanning set of a subspace can be reduced by removing vectors, right? We've already have seen that with that process, right? So you can always throw out vectors that you don't need. You can pare them down. You can also start with a linearly independent set and build up to a basis, okay? And then we make this observation here that if the dimension of a subspace is K, then if you have fewer vectors than the dimension, they cannot span S. If you have more vectors in the dimension, they can't be linearly independent. And if you have the same number of vectors as dimension, the only way they span is if they're linearly independent, right? So those are 3 things that's kind of articulated in one setting that we've been saying over and over again through this chapter. All right, so give this idea a go, right? So it's nothing different really in terms of concept. It's just now you're looking for the smallest number of linearly independent vectors that span a space, right? So that's the difference, is smallest number. And there are different ways of going about doing that, right? So go ahead and practice that with these homework problems in 4.2, and then we will talk about them before leaping into 4.3 next time. Okay, take it easy.